There we go.
This is Matthew.
Hi, guys, listen.
Oh, it works.
Hi. Can you hear us? Hello. Can you see everybody? Yeah, we can see everyone. Hi, how you doing? Hello. We've got a couple more things. Oliver Price. And Oliver, he likes comets, so he's going to tell us all about comets today. So without further ado, we're going to start his presentation. So let me just share my screen, and you let me know if you can see it.
Yeah. Yes.
Okay, brilliant. Oh.
Yeah.
Sorry about that. It's a bit. There we go. And can you see the slides? Yeah. Okay, perfect. Right. So, carry on.
Okay. So, I think it's a picture of hail block.
Yes, it is. Yeah.
So this was around when I was, I think, 4 years old, and possibly before you were born. And this is a really famous example of the comet. It has these bright two tails that you can see. And one of them is a blue tail, which is a plasma tail. That's what you're seeing there is carbon monoxide being ionized. And the white tail is the dust tail, which is a bit of a boring name, but that's what I study here in my PhD at Mullard Space Science Laboratory. Can we have the next slide?
Yeah, sure.
So I like to start with a question. Which one of these is a comet and why?
Oh, I know which one. I know what they're doing the asteroid. I heard what they're doing the asteroid. I think that's the black one. No. I'm just saying. Left or right?
Right.
The one that looks like it's got a lens flare.
Does the screen share make everything different?
Tom, you could just say right.
Yeah, it's the one on the right, Tom.
One on the right, yeah, I know.
Yeah. Okay. Yeah, it's the one on the right. So this is anyone know the name of this comet actually?
The one with Rosetta.
Yeah. So this is Comet 670 that Rosetta visited. And the reason you can tell it's a comet because of the jets of dust that are coming off it. So comets contain ices that are volatile. So when they come near the sun, they switch on and they start sublimating. So sublimation, when you have an ice, normally you expect it when it heats up to melt to a liquid, but sometimes you can go straight from being an ice to being a gas if you've got the right conditions. So comets, you get sublimation where you're going straight from ice to gas. That's releasing. You've got these jets. So this is, you're seeing carbon monoxide, carbon dioxide, water, and ammonia. Those are the main volatile components. And then also comets have dust in them, so they're dirty snowballs. They're usually referred to as, and these gases are dragging the dust out with them. So these two components, the gas and the dust, those are what then form those two tails that we saw in the earlier slide. And the asteroids are just rocky. So well done, you got that right.
Next slide.
Yeah, next slide. The other distinction about comets is that they have very elliptical orbits, right? So this is the orbit of Comet Halley, which comes past every 76, I want to say, years.
Yeah, I think so.
And it goes right out to where Pluto is, and then comes all the way back into the inner solar system. Whereas asteroids, they have generally circular orbits. Most of them orbit in the main asteroid belt between Mars and Jupiter, although some of them are a bit nearer to us, and then we watch out for those because they're nearer asteroids, so they pose a bit of a threat to us.
It's interesting here, Ollie, as well, looking at how bunched up all the planets, our neighbours are, right close to the sun. So these comets are coming from a long way out. Yeah.
So comets come from the far reaches of the solar system. So from two regions. There's the Kuiper belt, which is the region of objects that exists, kind of starting at Neptune, basically. So now Pluto, as a dwarf planet, is incorporated into what we call trans-Neptunian objects. And then further beyond, there is the Oort cloud, which is, instead of just being a disk in what we call the ecliptic plane of the planet's orbit, you have a sphere of rocks and objects all around the solar system. And this is stretching out to sort of almost, I think, sort of 2 light years.
Yes,
yeah. So this is going to sort of extending right out towards the nearest stars. So the solar system, what we define as a solar system, is actually much bigger than just our 8 planets orbiting close to the sun. Yeah, so have you all heard of the European Space Agency?
Yeah.
Brilliant. I always like to check this because we have, in the European Space Agency, a bit of a PR problem, I think, sometimes. Is that fair to say?
Yeah, I mean, well, NASA is flashy, isn't it? Everybody knows NASA, but European Space Agency is obviously a bit younger, but it's obviously done some really amazing scientific missions, and I think the Rosetta mission was a real crowning jewel in their most recent achievement.
Yes, so the Rosetta mission was an ESA, European Space Agency mission, that launched in 2004. So I find this fascinating because when I was not where you are, when I was younger probably than you all are now, this mission was launching. And yet I've been able to, as a scientist, a young scientist, early career scientist, still be able to work on this data set and partake in kind of the science and the conferences and all the fun of being a scientist.
So, yeah, so that's the thing with these space missions. They take so long to plan and launch that stuff that's being launched while you're the age you are now could potentially be, if you want to go into planetary science or space science, could be the data that you're working on in the future.
Yeah.
It's nice. It takes a lot of patience and a lot of forward planning, but high risk, high reward.
Yeah, and I think personally, when you learn about calculus or maths in school, it's all things that were invented 300 years ago or whatever. Not to disparage, maths is very important, but that's what really sells space science to me. Anyway, the Rosetta mission has this Philae probe, the little lander, about very small, kind of washing machine sized maybe, and that was really cool because it went down to the surface and then it fired these harpoons and it tried to cling on to the comet. But actually that didn't work so well. So it bounced about and it ended up in sort of a gutter underneath a cliff. And they spent a long, long time looking for that. I know, because I went to some of the meetings and they were like, we still not found it, we still not found it.
Yeah.
And in the end, they just about did find it. Which I think is an interesting story about how scientists don't know everything. Because I mean, this comet is maybe 5 miles across. It's really not big, and yet they still managed to lose their expensive probe there, which is a shame.
Next slide.
Yeah. So yeah, I mentioned a bit earlier about what comets are made of. So you've got these dusty, aggregatey, dusty particles inside this kind of icy snowball. And there's also lots of the other interesting kind of like chemicals and things there. Do you want to say something about this, Jacko? I think it's...
Yeah, so one of the reasons that comets are pretty interesting is they often have a lot of organic molecules on them, or things that contain carbon. And as you probably know, all life that we know of on Earth is carbon-based, and carbon tends to be very good at forming long chains and being able to bond with lots of different things. So it's considered quite important in the field of astrobiology, or looking for life in the stars, which is kind of what I do. And I mainly work looking on the planet Mars for stuff. But comets are very interesting because they may well be responsible for delivering some of these molecules to other planets, and we'll talk a little bit about that later. And plus, they're zooming around, flying about in space. and traveling long distances, so they might be quite a good vehicle for moving these things around. And recently, especially with the Rosetta mission, they found more and more organic molecules. And yeah, they're really important to know about if you're thinking about habitability and looking for signs of existing life, or looking for what could be the building blocks of life.
Yeah, I think I would add to that. That's a good explanation. That yeah, they are the original building blocks of the solar system, right? So what we know today on Earth, and even when we look on Mars, is really, really processed material, because essentially the sun is like a big oven, right? So the solar system starts with kind of all this dust and gas floating about, and that's like, if you're making a cake, you've got your kind of flour and eggs or whatever, and eventually that gets cooked into your nice like pasty things where life can exist, that is your Earth and possibly your Mars earlier in the solar system. But the comets and those outer, what I talked about, the Kuiper belt and the Oort cloud, because they're far away from the sun, you've not kind of processed this material, right? So it's still kind of left over from your what's called the protoplanetary disk. And so when these comets do get sort of disrupted and then they come in on their elliptical orbits to the inner solar system, that's our chance to study where we come from, essentially.
Yeah, chance to get a look at the ingredients.
Yeah.
And that's the other good thing about asteroids and comets, is it's like looking back in time to what would have formed the solar system. And this can tell us a lot about other solar systems as well, because then we can look at how we can see other solar systems that are in that process of forming from these protoplanetary disks, and try to get a much better idea, not just of our own planet, but of our solar system and beyond, to other places in the galaxy. So comets are cool. I love comets. Oh, so Panspermia. So I alluded to this a little bit earlier. So there is a theory called Panspermia, which comes from the meaning all seed, that possibly life may have originated elsewhere, either on another planet or even coalesced within space, and you start to get carbon bonds and maybe amino acids or other interesting chemicals, like there's one that I study called the polycyclic aromatic hydrocarbon, or PAHs, and they're considered quite important. And these just form in interstellar space, and they're also found on comets. But Panspermia goes a step further and suggests that maybe life might have formed elsewhere and then been distributed throughout other solar system, or even further throughout the galaxy and the rest of the universe, from one source. And that if we do ever find life on another planet, it might all be related and have a common ancestor. So Panspermia doesn't really tell us about the origin of life, but more the distribution. So if you had, for example, a planet that exploded or something happened to it, and the rocks went off through space and the dust was around, and it already had microorganisms on it, and we know that microorganisms can stay dormant and survive in extreme temperatures and low pressures and high levels of radiation, that it might then be distributed around. So if we do find microbial life on Mars, for example, our next door neighbor, what will be crucial is it related to life on Earth? And if it is, then it must have somehow come to both planets from a single source. So we do have Martian meteorites on Earth, and we believe that there will probably be bits of Earth rock on Mars from early solar system collisions and stuff, but it's also possible it came from further out. And so Panspermia kind of talks about the delivery of life to multiple planets. And it'll be interesting. The next question, if we ever find life, will be, is it all related? So yeah, 67P, the Rosetta mission, they found 16 types of organic molecule. And interestingly, they found 4 brand new ones that they'd never found on comets before. So, you know, this is really just scratching the surface. This is one mission to one comet that found all this interesting information. And, you know, there are countless comets out there. But I mean, Ollie, maybe you can tell us a little bit about why it's quite difficult maybe to predict when comets are coming in and to plan missions to comets.
Yeah, okay. So, so this is 67P is a short period comet. So it orbits the solar system, the sun, once every 5 years, I think. And it was easy to get to. Well, not easy to get to. I mean, it took, what, 11 years to get to it. That's not too easy. But it has a it's orbiting close to the ecliptic plane. So if you think we're orbiting here, the orbit of 67P is maybe something like just a bit off. Because to do plane change maneuvers is really expensive when you have a rocket. But other comets can have any kind of what's called an inclination. So this angle between the various kind of orbits. So they can even orbit retrograde. So that's the wrong way around in the solar system. So it's challenging to get a spacecraft onto those orbits. And then also you get long period comets, which maybe come into the solar system once every 20,000 years or something. So, I mean, these are coming from such deep space that, because they're not active when they're far away from the sun, so they're just rocks, so we can't really see them. It's really, really difficult to predict, basically. So we rely still a lot on ground-based studies.
Yeah, and just going back to some of the chemicals, so those polycyclic aromatic hydrocarbons I was telling you about, these are what they can look like. And you see that bottom one, coronine. What's quite interesting about them is they can form sort of little balls or bubbles. And this is important in how life might have started, because we think that the cell wall was probably very important in how life started, so that you have a barrier between the inside and the outside, so any emerging biochemistry is protected from the outside. And so comets also provide a good place for that, because you've got dust trapped within ice, which can protect any microbes or organics within the ice from damage from ultraviolet radiation, not only emitted from the sun, but from other stars as well, where they're flying around in space. So comets are a pretty good vehicle and vessel for keeping things safe from radiation.
Where do we find polyaromatic hydrocarbons?
Oh, everywhere. So polycyclic aromatic hydrocarbons are, if you made toast this morning, and especially if you burnt that toast, you would have had some on your toast, because they're the byproduct of partially burnt organic material. So on Earth, they're absolutely everywhere. Anytime you burn any wood, coal, food, anything organic with carbon in it, you'll get PAHs. But they've also been found just floating around in space and just coming together in space. And it's thought that, I think it's around 20% of all cosmic carbon that they've observed in the universe is a school bell, I think. Right, so I think it's time for 3D glasses.
Yeah.
So if you can all put on your 3D glasses. And then we'll go to the first image. I think it works best if you put blue on the right eye.
Yeah, I think that's...
Yeah, blue on the right eye.
Is that working?
Does it look good at your end? Can you see it?
I don't know what we're looking at.
I don't know. We're looking at the comments on the screen.
Shut up.
I think we had a question, but we had a lot of feedback.
Oh, okay, yeah. Question.
Adele? Does the 67 on the 667P stand for the number of the comet that you found? Or what does that stand for?
Yeah, that's great. So every comet that we see come past us twice is given a number like 67, or for example, Halley is 1P Halley. So 67P would have been the 67th comet that they found, that they confirmed that it had like a multiple orbits, basically. There are comets where we only see them come past once, so there's a different naming convention for that, which is a bit more complicated. But I won't bore you with the details.
Some of the comets end up with quite dramatic ends. So I think, is it Shoemaker-Levy?
Yeah.
What happened to that? Can you tell us about that?
That one crashed into Jupiter.
Yeah.
So it has a... So P is for periodic, but you can, I think Shoemaker-Levy has, is it X or is it D, I think? Maybe D for destroyed, destruction.
Yeah, you can see, if you look up Shoemaker-Levy, you can see images of that smashing into the surface of Jupiter and leaving behind big holes in the cloud tops, which is pretty impressive. Yes, that was a good question. It's interesting to know these naming conventions.
And they're named after the discoverers. So 67P is Chury, Imhoff, Gerasimenko, I think.
Yeah, so which is often, people often call it 67P.
From Russia, yeah. It's
easier to pronounce. So yeah, can you all see, if you put your glasses on with right eye blue, is that showing up as 3D to you?
Oh, right have no idea.
Oh, yeah, it is.
Yeah? You sometimes have to zoom in a bit and scale it a bit, but you should be able to see it move around a bit. So, Ollie, you want to talk us through this image?
Yeah. So this is the image I showed you earlier. And you can see the sun illuminating the top of the comet, and you're getting that really, really strong, very, very directional jet of gas and dust coming off. And when we talk about the results from the Rosetta mission, when we talk about the detection of those organic materials, we're essentially flying through those jets. So most of what we learned is from studying this region called the Comet. So that's the nucleus. It looks a bit like a rubber duck. And the sort of envelope around it is the Comet. And yeah, do you want to tell us about the important results that they found when they flew through this? I mean, you've told us about the organics. I'm putting you on the spot here.
Yeah, you are putting me on the spot.
Yeah, okay.
About?
So they were looking at the water. They wanted to see did the water they found here match up with the water on Earth to sort of find that more origin of life. And I would say the biggest result from this mission, from flying through these jets, is they found that if you look at the isotopes, have you learned about isotopes yet?
Yeah.
So the various isotopes of water, you can look at the ratios between them, right? And you can sort of put like a little label on each of your different samples of water to say, okay, it's got this much deuterium versus this much hydrogen. And the water they found at 67P is not similar to the water you find at Earth. And then they can do a calculation to say, okay, let's suppose the water we have on Earth is delivered by comets crashing into the Earth. And what ratio of deuterium would we expect in the Earth? It doesn't match up. So then they can eliminate basically, or 67P like water delivery.
Because it's a bit of a mystery still how we've got so much water on Earth, because in its beginning formation it would have been a big molten ball of lava, and so a lot of water would have been boiled away, and this is before it had a proper atmosphere and a water cycle and stuff to maintain it. So there's arguments you get hydrated minerals that have got water trapped in them, and some of it could have come through that through various geological processes. But it was often talked about that our water all came from the delivery of ices by comets, and so the discovery of the deuterium ratios at 67P are a little bit of another question mark. And that's the thing about science, is that for every question you have, once you find a way to answer it, you've got another 100 questions probably. Yeah. So you'll never be out of a job if you want to be a scientist, because there's always more to discover.
Just a quick question.
Is it true that no matter what point in its orbit a comet is, the tail will always be facing away from the star?
Yeah, that is true. That is the plasma tail, also known as the ion tail. So that is the gas, those volatiles, the water, carbon monoxide, When they get ionized, and then there's a stream of plasma coming off the sun, and they're sort of joining that, and then they're just getting pushed away from the sun. So no matter where you are, you're right. The ion tail, the plasma tail.
Can you just remind us, and for anyone who's watching on YouTube, what an ionization is? Yeah.
Okay. I'm not sure if you've learned this yet, but plasma is the fourth state of matter. So when you turn on your Bunsen burner, that's plasma. It's gas, where the atoms, so you have the electrons orbiting a positive nucleus, those have separated and they're sort of free to sort of move about on their own.
So the electrons have been taken away from the nucleus.
So you're free to conduct sort of currents and interact with magnetic fields and things like that.
All sorts of interesting stuff.
And that's what a lot of people here at the lab study, is these magnetic field of Earth and magnetic field of Sun, and how the plasma is coming and interacting in all different places, and it's a nightmare.
Let's go to the next picture.
Yeah. So So this is a closer picture of the surface of 67P. And you can see it look quite a lot like the moon. So that's telling you you've got an old surface because you've allowed craters to build up in some parts. But it's actually a mixture because you've got that kind of in the middle, this old surface, but you've also got a kind of smoother bit that looks like sand dunes. You've got a lot of boulders in the north of this image, and generally quite a lot of texture. So comets actually have kind of really, really varied surfaces actually, because you have different parts being active. And so when you're active, you're releasing your gas, right? And then you're sort of renewing the surface material. You've got these, I think in the bottom there, you've got like a kind of almost a cliff type structure. Do you want to tell us something about cliffs?
Yeah, so I think we've got one more image, and then we can go to
so this is sort of similar. You can see that you've got this whole region on this limb is kind of almost like, it looks like a sand dune, and you've got barely any craters. So cratering, I mean, really important for pretty much diagnosing how old planetary surfaces are. So the Earth, you don't have any craters. You do have craters on the Earth, but from the space, we know that our surface, our tectonics is refreshing that. If you look at the moon, it's just all craters, right? So you know that.
It's a very good proxy for how old the surface is crater counting, and people make a whole career out of literally counting craters or finding automated ways to count craters to try and age the surface. One more.
We've got another really nice cliff here as well.
Yeah. Because, it's interesting, a lot of these look like they could be on Earth, which is, what we have to do in order to study these things. We have to make comparisons to what we know on Earth. So a lot of people from physical geography and geology work in planetary science as well as physics. So it's not just maths and physics people. It's geomorphologists, people that understand geological processes and geographical features that we find on Earth.
Because you've got in the top right, that kind of loose rock and scree almost looks like something from the Lake District. I think. Yeah,
definitely. So cliff collapse. If you can see this GIF moving backwards and forwards, this is a couple of images to show the changes in cliffs. And so, as Ollie was talking about that sublimation process, where it goes from a solid to a vapor, causes not just dust particles to come off slowly, but sometimes these sort of catastrophic mass movement events, we call them, where you get a big lump of something collapsing and falling down. And this is really interesting because it has ramifications for exposing new material in ways that we see in other places in the solar system. So one of the things I study is the south pole of Mars, which has a permanent CO2 ice cap and undergoes these same sublimation processes. But rather than, as with comets, it's as they come in towards the sun. With Mars, it's seasonally as the South Pole is exposed to the sun in its spring and summer. And we see these sublimation pits forming with scarp walls and cliff walls that then collapse in mass movements. And you actually see the same on the North Pole, a lot of mass movement, rock falls and exposure of new material. And there were some images from cliff collapse from the Rosetta mission where you can see clear differences as the cliffs collapse. And it also seemed to be partnered with eruptions of dust and gas suddenly being exposed, and huge areas of bright material being exposed that were several times brighter than the rest of the comet's surface, and then would gradually fade over time. So it's a really nice way to look at what's under the surface, because we clearly can't go and dig a hole as we would on Earth to find out what's underneath, but nature does it for us and essentially excavates new material for us to find, which is it was a very interesting and I think unexpected result from the Rosetta mission. And
I think these cliff collapses were linked to the very directional jets we saw in the first image. So I think they sort of drew parallels by saying, like, you get a collapse and then you're releasing, I think in that image, if you go back a slide, Jacqueline, you can see that material that's been exposed is whiter because it's probably got a bit of a higher concentration of ices relative to dust. And then those have been linked to kind of those active regions which spew out a load of material. So it was really important to kind of pair what we call remote sensing, so that is to look down on the surface of our cameras and isolate the different bits, with the in situ studies. So in situ just means you're just looking up the properties and the materials where you are at the time. So the things you're flying through with your main spacecraft.
Yeah. So it's as always, it's a mixture of different disciplines and skills to find out the bigger picture. So although science, you can end up being quite narrow in what you study. There's always collaboration between different fields to establish the bigger picture, and then beyond this comet, the bigger picture of our solar system, and beyond that of our galaxy, and so forth. So space science goes from the very, very big to the very, very small, and that's why it's cool. So I think, we're at the end. We've got our other school online. I'm just going to stop sharing my screen so you don't get this weird thing going on. And yeah, I'm just going to check. I think we've got a couple of questions from our other school. Let's see what they've got to say. How many years before we can see a comet? Oh, that's a really good question. So yeah, when's the next comet we're going to see? Are we putting you on the spot here?
Yeah,
Really?
so it's almost impossible to predict, because that 67P, if you look at it from Earth, it's like a tiny dot. It's very, very faint. You need a very, very powerful telescope to look at it. In terms of those comets like Hale-Bopp, or I've heard of Comet Naught, which are the really, really bright ones that you can see just with the naked eye on the ground. Those, because they're coming from so far away in the system, they come past once every 20,000 years or something, and then they're only active, they're only sublimating when you're near the sun. Basically, it's impossible to predict, because they're just completely dark and turned off, and then all of a sudden they light up. So you maybe have half a year of warning sometimes, I think, because you're trying to spot them like when they're very, very faint, so you can get them before. So there was that object, Oumuamua, I think, is that right? That was an interstellar object. So it was like a comet. It came in, but it had the orbit suggested that it was actually from outside the solar system, and we only spotted that after it was already heading away from the sun. So it came all the way past, and it was just too faint for us to see. Although it was more like an asteroid, so it doesn't have a bright tail. But it's very difficult, basically.
But Halley's Comet is irregular, right?
Yeah,
but
so Halley's, I think you've got to wait 50 years.
Yeah, so you should be around.
It'll be fine.
That, yeah. Have you got any more questions from Wellington School?
Did we have another one in the chat box?
Yeah, we do. Go ahead.
Do you think space mining will ever be profitable?
Sorry, I didn't catch that. Can you say that again?
Do you think the mining of asteroids will ever be profitable?
Mining of asteroids? Yeah, I think it will.
Yeah, totally.
Yeah.
Because I happen to know there's one asteroid that's just chock full of like gold and platinum and silver. So this is not comets. This is like, you're right, it's asteroids. But there are asteroids that have a lot of valuable metals, and also I think like rare earth elements. So
they use those in phones
that
and
you
stuff.
need to build electronic circuits and smartphones.
Also things like helium is in short supply because it's a noble gas and it's inert and doesn't combine with anything, and it's very light. It flies off very quickly. And so we running low on helium, although people still use it for children's balloons. I'm surprised it hasn't been banned yet, but it's used for a lot of medical machinery like MRI scanners, and also in spacecraft because you can use it to keep things really cool. And there's tons and tons of helium-3 in the surface of the moon that's been trapped there from the solar wind. So people talk about, there's a couple of movies, I think that there's a movie called Moon where this is the premise. But I think what might stop that happening is if we technologically reach the point where we can synthesize any material from anything else before we need to do that. Alchemy. But, if we get to the point where we can create our own materials out of any atom, then we won't need to fly off and do things. But I think that's probably...
I think we'll be mining asteroids.
We'll be mining asteroids before then. Especially with the privatization of the space industry becoming more common. I think we will see missions there for monetary purposes. Hopefully we'll get to do a lot of science alongside that, rather than just sending up people to work there. But who knows? Who knows what will happen? We'll have to wait and see. And we had one more question from our other school. So they asked how unstable are the surfaces of comets in terms of cliffs and stuff?
Yeah, so really unstable, basically. I think you're losing, every time you go past on that rock, it's shrinking down slightly because the ice is just sublimating away. So I think you lose, I think, a few meters worth of surface. So it will be like you're standing on Earth and then the ground's going down by sort of a couple of meters every 5 years you're going around. Although it's much smaller than Earth. But yeah, these events, these cliff collapses, these pits forming, this is happening like constantly, basically.
So what's happened to the land there? Is it like fallen even further down a ditch, or?
I'm not sure, because they only just about they rescued it, and then they basically had to they went behind the sun is what happened. So the comet was what's called opposition. So the Earth is here, the sun is here, it's the other side. So they weren't able to communicate with it, and it was getting further away. So they essentially ditched the main orbiter into it just crashed into the comet just to see what would happen.
I think we've got time for one more question from Wellington, if you have one, before we go.
Do you think vibranium will ever be real?
And you know, that's an interesting question. So the guy who came up with the concept of the periodic table, Mendeleev, he essentially predicted elements that we haven't yet discovered. So we kind of knew before we found them what electron arrangement would be in each type of element, and also what kind of properties it would have from which group it sat in and what it would like to combine with. And I don't think there's a space for something like vibranium.
Vibranium, Black Panther.
Yeah, and Captain America's shield.
I've not seen that.
No spoilers for Black Panther.
I'm a Star Wars guy.
Oh yeah, you could be both. You can be both. But that's, you know, something like that is an element. But whether or not our material science will develop well enough for us to develop things that are similar to these sorts of properties is interesting. And actually, there's a thing called a Whipple shield that they put on spacecraft to absorb anything that comes at it and stop damage of the actual spacecraft itself. It can't be transparent, so it's no good for lenses or windows, but you can put it around the rest of the spacecraft, and when space junk or bits of asteroid and stuff in space hit it, it deflects all that energy and protects what's underneath. And those things are traveling at huge speeds of like 11 kilometers per second and stuff when they hit them. So Whipple shields are, you know,
I'm really
kind of on
glad
the way.
you brought that up, because what was his first name? Whipple.
I don't know.
He was a NASA engineer, but he came up with the dirty snowball model of comets. So he's like,
what are the odds?
So
yeah,
really brainy guy.
Yeah. So yeah, fingers in all sorts of pies. I think we've got to end it there, but we just want to say thank you to both of our schools so much for joining us. They're really interesting questions. And I know that St Cuthbert's wanted to have another look at the 3D images, so we can email those over to you. And we can also send you some 3D glasses as well, so that your students can have a look at them and you can print them out and have a look at them.
Also we didn't show them, but there are some 3D movies.
Yeah, there's lots of 3D movies. So yeah, thank you so much for joining us, and do let us know if you have any requests for any specific topics, like if you're interested in finding out more about what's in asteroids to mine them, or anything we've spoken about, engineering, whatever. We can find an expert like Oliver to deliver us another talk. So yeah, thank you so much.
Thank you.
Bye. See ya.